Okay, now we're at our last method of heat transfer. It's actually radiation. So, how does radiation actually occur? We learned that previously conduction and convection requires a medium for transfer. So, liquid or gas or solid, okay, definitely particles are needed. Okay, particles are needed. However, if you think about it, between the sun and us is space, and space is actually vacuum. Your space there is actually a vacuum. So how on earth does the sun transmit heat to us on the earth? Okay, it's actually by this process called radiation. So the sun gives out heat energy to us via radiation. So what is radiation? You can see here is a continual emission of infrared waves from the surface of all bodies transmitted without the aid of a medium. So the definition is a little bit tough here, okay? A lot of things to remember and some of the weird names you have never seen before. Continual emission just means continuously releasing or giving out. Emission means giving out. Okay, giving out. Infrared waves, okay, infrared waves is just a type of wave. And then so in radiation is a given of infrared waves from the surface of all body. Take note, it must be from the surface. Okay? And is transmitted without the aid of a without the aid of a medium. So this is for your radiation. So electromagnetic waves, obviously, just now as we said, is actually your infrared waves. Okay? The one that we talk about radiation here is actually infrared waves. It makes us warm. So the thermal energy transfer infrared wave is called radiant heat. Okay, a lot of difficult, not so difficult term, but new terms here. Don't worry too much about it. Just know that radiation produces infrared waves, which keeps us warm, which produce heat. Okay, now one interesting thing here is that the hotter the object, the greater the radiant heat is emitted. Okay, so for a sun, it's very hot, so there's a lot of radiant heat being emitted. Now, and obviously all objects and surfaces absorb infrared radiation, and this absorption causes a temperature to rise. Okay? Now, so let's try to look at some of the application here. We talk about the rate of radiation. Why is our school uniform usually white in color or in lighter shade? The key here is this. You want to talk about whether an object emit or absorb heat. How fast does it absorb or emit heat in terms of radiant heat? Okay, radiant heat is based on three different things. Temperature. Hotter temperature emit more heat. Okay, darker, duller surface absorb and emit heat better. And the last one, we talk about surface area. The larger the surface area, the greater the emission of infrared radiation. Let's look at one example. I got a sun over here, a black dull flask, white shiny transparent flask over here. Because this is black, it will absorb heat faster. Whereas this one is silver or white, it will not absorb heat as fast. So take note, the color of the surface does matter. Okay, black is a good absorber of heat. Okay, it's also a good emitter of heat actually. So you look at the next one. Okay, which flask will cool down faster? In actual fact, the black one will also emit heat faster. We say initially it will absorb heat fast, but the same type of surface, the black one will also emit heat fast. Right, so black surface is a good absorber and good emitter. So black surfaces are good absorber and emitter of heat. Okay? So now, obviously from here you can see that we talk emitter and absorber. Dull black surfaces are the best. Whereas for the, you want to talk about worst emitter, worst absorber, silver is the worst. Okay? Then reflector, try not to use this term here. It may be a bit confusing. So generally we tend to use emission and absorption. We try not to use the word reflect. But do note what it really means here, okay? Just know how it means, but generally we will always use these two terms, emission and absorption. So looking from the data just now, we know that a good emitter is also a good absorber of radiant heat. Then obviously the other way around, a poor emitter is also a poor absorber of radiant heat. So let's look at some examples. So you can see the solar panel here. Solar panel, they are generally dull or they are normally black in color. Why are they black in color? Because we want them to absorb the energy from the sun, the heat from the sun. So we tend to use black because they are good absorbers of heat. So the solar panel absorbs heat from the sun and converts into electrical energy. We use black in color. Next one, okay, this is actually a cooling fin behind the refrigerator. Okay, now you realize it is black in color too. Why? I want to cool things down. I want it to emit heat via radiation fast. So obviously, if I want it to emit heat fast, I will use the color black because I know black dull surfaces, they are good emitter of heat. Okay, good emitter of heat. So therefore the refrigerator will be kept cool. This is the application for dull black round surfaces. Okay, how about for shiny silvery smooth surfaces? So example, our uniform, they're normally white or lighter in color because we want our uniform to be poor absorber of heat. But you can imagine if our uniform is black in color, it will absorb so much heat, we'll be feeling so warm, we'll be feeling so uncomfortable. So that's why it's a good design that our uniform is generally white or lighter shade because they are poor absorber of heat. Next one. Teapot is generally shiny and silver because we want to reduce the heat loss from the content. Silver and shiny surface, they are poor emitter of heat. Your teapot here, you generally want them to retain the heat, correct? You don't want them to lose the heat so easily. So we put them as shiny and silvery so that the heat is not lost to the surroundings so fast. Next one, we have our glass house. Okay, this is we put it as glass because it is a good reflector. Okay, now for the glass house is a little bit we are more focusing on the reflection of infrared waves. Okay, not so much about absorption and emission. It's really a lot more about reflection. Okay, so when the infrared waves can come in, they will generally get trapped inside here, and the greenhouse will generally be warm. And the last one, okay, we talk about a summary of all the various method of heat transfer. So a thermal flask is actually using all of this here. A stopper is made of poor conductor, so it can help to keep our hot content inside warm because poor conductor, okay, reduce heat transfer. Wait, don't say reduce heat transfer, just say reduces rate of, let's use rate, it reduces rate of conduction. Okay, now the glass walls are silver and highly reflective. They minimize heat loss due to radiation. In actual fact, in between the glass wall is double wall glass and inside there's a vacuum. This vacuum also helps to prevent conduction and convection. Take note of the word reduce and prevent. Prevents means does not take place. Okay, reduce means it does take place, but it doesn't function so well. So stopper per conductor, so reduce rate of conduction. The silvery here, the silver surface, inner glass silver surface, minimize heat loss due to radiation. So minimize here means it does happen also. And the last one we talk about vacuum between the double glass wall. Okay, this prevents conduction and convection. So you can see a thermoflask uses conduction, convection, and radiation. Conduction, convection, and radiation. The principle of it to help to keep our contents warm or cool. So this marks the end of the transfer of thermal energy. So do take note of the applications over here. You must know the applications. Okay, obviously to know how to apply, in order to apply, okay, you need to know how the three method of transfers are related. So, yep, this marks the end for this chapter over here. So that's all.